Welcome, learner. Today, we are undertaking a deep dive into the very fabric of modern technological infrastructure.
But we're not looking at, the physical wires or the turbine.
No, not at all. We're looking at the mathematical blueprint that actually made them all possible. Our source material for this is truly foundational, Charles P. Steinmetz's Engineering Mathematics, and we're looking at its crucial 1911 and 1914 editions.
Yeah, this text represents a real moment in history, a point where the mathematics being taught in the classroom fundamentally failed to meet the needs of the emerging electrical industry.
And Steinmetz was right at the center of that.
Absolutely. Steinmetz, who people often called the Wizard of Schenectady because of his work at General Electric, he was facing a crisis. He saw that for the electrical age to really take off, engineers needed a new kind of guidebook, one that bridged abstract mathematical theory directly to practical, reliable, and efficient calculation.
Okay, let's unpack that right away. When we hear that engineering students were sadly deficient, what does that truly mean? I mean, were they just failing calculus? Or was the material they were learning simply irrelevant?
It's a great question. It wasn't that the students were, ignorant of general mathematics. They were often quite proficient in it.
Right.
But Steinmetz saw that they lacked familiarity with these crucial, very specialized branches of math. And the main one was complex algebra, that had become absolutely essential for analyzing alternating current systems. He was blunt about it. He said that trying to apply standard general course mathematics to real electrical circuits led to, and this is his quote, apparently hopeless complication and almost endless calculation.
So the mission of this book, then, wasn't just to teach math. It was about teaching the most efficient way to calculate real-world physical systems. It was a kind of manifesto for saving time and reducing errors.
Exactly. Mere theoretical knowledge is not enough for an engineer. The engineer needs the ability to apply it, to carry out the numerical calculations with speed, and most importantly, to ensure the results are reliable. This text is heavily focused on the methods of calculation, the efficient use of curves, and just generally boosting the productivity of the engineering staff by giving them the right tools for the job.
So Steinmetz was basically selling efficiency and reliability all wrapped up in a math textbook.
That's the perfect way to put it.
And we know his methods were so critical that they needed updates almost right away. So what key additions did that 1914 revision bring to this applied engineering canon?
Well, the 1914 preface really shows that Steinmetz was constantly refining these practical tools. He added discussions on some pretty sophisticated topics like the use of chain fractions, which is a very convenient method for, numerical representation and approximation. It helps engineers quickly find fractional relationships. He also included a brief but really important mention of Diophantic equations. These require integer solutions and are useful in certain design and proportionality problems. And maybe most critically, he formalized the need for different kinds of engineering reports. He understood that the best calculation in the world is useless if you can't communicate the findings properly to the right audience.
Let's dive into the philosophical core of it then, the pivot that really defines electrical engineering math. This expansion of the number system. Steinmetz starts with the very basics, right? Addition and counting get us positive numbers.
Yes, and then subtraction immediately forces us to invent something new.
How so?
Well, subtraction reveals the first great limitation of just counting things you can see. If you're counting positive objects, like, say, 5 meters of string, you can always add 3 more meters. That's easy. But if you try to subtract 7 meters from that 5-meter string, the operation is physically impossible. You run out of string.
Right, you can't do it.
So to solve this purely mathematical impossibility, we introduce the concept of negative numbers.
And this is where Steinmetz takes what feels like a really radical stance. He calls the negative unit, -1, a mathematical fiction. Now hold on. If I have a debt of $1,000, that negative balance feels extremely real to my bank. How can he possibly call it a fiction?
He clarifies what he means by fiction. He's contrasting the mathematical construct with universal physical experience.
Yeah.
In many physical realities, the negative unit just doesn't exist.
Like what?
Take light, for example. If you have 5-foot candles of illumination and you subtract 3, you have 2. But you can't subtract 7-foot candles. The physical limit is 0. Darkness. You can't have negative 2-foot candles of illumination.
Okay, that makes sense.
And it's the same for weight, or, the length of that string. In these cases, the negative number is what he calls the mere imaginary mathematical fiction, because it has no direct, universally corresponding physical quantity that you can derive from counting or measuring.
That's a crucial distinction. It's not about things like debt or temperature, which are relative measures on a scale. It's about absolute quantities that you get from basic measurement.
Precisely. And he contrasts that fictional application with the scenarios where negative numbers do have a clear physical meaning. Temperature is the classic example, right? 5 degrees above freezing minus 7 degrees leads to 2 degrees below freezing, which is a real state of physical existence.
And time, longitude.
Exactly. Time, latitude, longitude, financial assets, and liabilities. They all operate in two opposite directions on a single line. The negative sign just indicates a direction relative to some arbitrary 0 point. But even in those cases, Steinmetz emphasizes that the concept is a mathematical invention, one that's necessary for the rules of algebra to work, not something that you derive directly from the act of counting positive units.
Okay, that sets the philosophical table for the next revolutionary step, the quadrature number, J. We're all taught in school that J, or I, in math class, is just the square root of -1. How do you take that mathematical oddity, which can't exist on the number line, and turn it into the physical tool that can power a whole city?
This is, I think, Steinmetz's most elegant stroke of genius in applying math to engineering. He uses the geometric interpretation of multiplication. So think about a number, say +5, just sitting there on the horizontal number line.
Okay.
If you multiply that +5 by -1, what do you get?
You get -5.
Right. And what has happened geometrically? The number has rotated 180 degrees. It's reversed its direction on that line.
So multiplication by -1 is a full reversal, a flip.
Yes. And if that's true, then multiplying by j, which is the square root of -1, an operation that if you do it twice gives you that 180-degree rotation, must logically correspond to a rotation of half of 180 degrees.
So a rotation of 90 degrees.
Exactly.
Wow. So the impossible operation of finding the square root of a negative number is actually the physically possible operation of just shifting the dimension entirely.
You got it. If your original positive and negative numbers run along the horizontal axis, multiplying by j transforms that quantity into a quadrature number, which means it now lies on the vertical axis, perpendicular to the original line. This quadrature number represents a direction that is 90 degrees away, so upward or downward.
This is the real aha moment for the engineer, isn't it? The imaginary number is only real when it points in a direction that we can actually physically measure.
And he's very clear that this concept only has physical meaning. In those cases where 4 directions exist, so left, right, up, and down, forming a plane. If you have a situation where only 2 opposing directions exist, like time, past, and future, then multiplication by j loses its physical meaning because you can't just rotate 90 degrees into a different dimension of time.
But for alternating current circuits?
For AC circuits, it's perfect. We deal with quantities like voltage and current that are constantly shifting relative to each other in time. These are phase angles, and they can be mapped perfectly onto a 2D plane.
And this combination gives us the foundational element for all of AC theory, the general number.
That's right. The general number, or the complex quantity, is simply the algebraic combination of an ordinary real number, which Steinmetz calls A in a quadrature, or imaginary number, JB. The form A equals a plus JB can represent any point in a two-dimensional plane using rectangular coordinates. It compresses 2 separate pieces of information magnitude along one axis and magnitude along the perpendicular axis into a single algebraically manipulable entity.
So a quick question on that. Does solving for higher roots, like the 4th root of -1, force us to expand the number system even further into more dimensions?
That's a great question, and surprisingly, no. Steinmetz shows that the 4th root of -1 still resolves into another general number, an x plus j. The result is simply a rotation of 45 degrees or 135 degrees from the horizontal axis.
So it's still on the same plane.
All of these points remain locatable within that single 2D plane defined by a plus JB. This two-dimensional system is completely sufficient for the rules of algebra, specifically multiplication and division, to apply coherently. And that's why it became the absolute workhorse of AC analysis.
So now we have A equals A plus JB, this single quantity that captures 2 dimensions. The big advantage here must be turning vector geometry, which is so laborious, into simple algebra. So how does this simplify combining and resolving AC vectors?
Oh, the simplification is just immense. Before this, combining 2 AC vectors, let's say a voltage drop across a resistor and another across an inductor, required drawing out parallelograms and using, time-consuming trigonometric laws to find the resultant vector's magnitude and phase.
A lot of room for error there.
A ton of room for error. With the general number, combination is just achieved by simple addition. You have two voltage vectors, E1 equals A1 plus JB1 and E2 equals A2 plus JB2. Their sum, which represents the total circuit voltage, is just E total equals A1 plus A2 plus JB1 plus B2. That single algebraic operation is the geometrical combination of vectors using the parallelogram law. It's faster, it's less prone to drawing errors, and it's far, far more reliable.
Okay, that covers addition and subtraction, and the rectangular form seems perfect for that. But what about multiplication and division? Those are essential for dealing with impedances. That requires us to shift perspective to the polar form, right? CISA cos plus Jason.
Yes, the polar form is where the physical meaning of multiplication just shines. When you multiply two general numbers, let's call them A and B, the result is achieved geometrically by two actions at the same time. First, you multiply their absolute values, which scales the length of the resulting vector, and second, you add their phase angles, which rotates the resulting vector.
So this means an impedance value, which is itself a complex number, Z ilk R plus JX, resistance plus reactance. It's not just a value, it's acting as a mathematical operator.
Precisely.
So when you multiply the current vector I by the impedance vector Z, you're simultaneously scaling the current's magnitude by the magnitude of Z and rotating the current vector by the phase angle of Z.
Exactly.
The complex number is no longer just a passive coordinate on a map, it's an active operator. It physically defines how the current shifts in both magnitude and direction relative to the voltage in an AC system. And that one algebraic step replaces what could be pages and pages of trigonometric manipulation.
And Steinmetz didn't just use this for electrical engineering, did he? He showed it had this universal utility for any 2D vector problem.
Yeah.
Tell us about that turbine example.
Yeah, that's a great one. In section 23 of the text, he includes this detailed anecdote about calculating the dynamics of a steam turbine. Engineers at the time needed to analyze the velocity vectors of steam as it passed through the turbine blades.
Which sounds like a very complex mechanical diagram problem. It was. The steam enters the bucket with a certain absolute velocity vector, which is then reduced by friction and redirected by the bucket's angle. Calculating the resulting exit velocity usually involved these really complex drawings. But Steinmetz showed that by representing these velocity vectors as complex quantities, they could be added, subtracted, and multiplied algebraically.
So instead of drawing out the parallelogram of forces for every single stage of the turbine, the engineer just inputs the velocity and the angle as an A plus JB number and lets the rules of the general number do the work.
Exactly. For instance, he calculates the absolute velocity at, I think, 1,255 feet per second. This is then combined with the tangential velocity component and the blade angle. By translating all of these vectors into the complex plane, the calculation for the resulting exit velocity becomes fast, clean, and reliable. It was a powerful validation of the general number beyond just electrical theory.
But all this power comes with a critical warning, doesn't it? Steinmetz is very careful to caution that mathematical operations only apply if the result has a physical meaning and, this is the key, can be represented in the same diagram as the factors. This limitation is really what separates a mathematician from an engineer.
This is arguably the most essential takeaway for any practical engineer. You have to always exercise judgment. Take the physically meaningless example we sort of touched on earlier. 3 horses times 4 horses. The result is 12, but 12 what? The operation exists in math, but the result has no physical reality.
And then there's the more subtle trap where the result is meaningful, but it breaks the diagrammatic rules.
The standard trap here is calculating area. 3 feet times 4 feet equals 12 square feet. Now, 12 square feet is a perfectly meaningful physical quantity. However, the result, the area, cannot be represented on the same line or in the same 2D vector plane as the factors, which were lengths. And furthermore, if you scale the units, say from feet to inches, the product changes disproportionately. You get 1,728 square inches versus 12 square feet. It proves that the algebraic relationship doesn't hold a consistent geometric representation.
And this brings us to the ultimate limitation for the electrical engineer using a plus JB, the power problem. Why can't we just multiply the complex voltage, E, by the complex current, I, to get complex power, P?
It's because of that exact rule we just discussed. The result of the operation has to be able to live in the same physical space or diagram as the factors. When you multiply two alternating quantities, I and E, the resulting instantaneous power, P, is fundamentally of a different frequency.
Oh, right, it's double the frequency.
It's double the frequency of I and E. So since power is oscillating at 2 times the fundamental frequency, whereas I and E are defined by the fundamental frequency, the resulting power vector just cannot be accurately represented within the single frequency polar diagram that defines I and E. The mathematical product, I times E, is rigorous, but it does not represent the complex power that engineers need to analyze in the circuit. You have to use different techniques for that.
So the algebraic shortcut works perfectly for, say, combining impedances and solving for voltage and current phase shifts, but it fails for power flow because the power is oscillating at a different rate and really in a different dimension. The engineer has to be constantly vigilant about those physical boundaries.
Absolutely. The math is a servant to the physics, it's never the master.
Okay, so we've established that the general number, a plus jb, is the perfect tool for 2D analysis, but real life is 3D. What happens when engineers try to apply complex numbers to space vectors? And why did Steinmetz dismiss the popular contemporary alternative, Quaternions?
Right, Quaternions were developed specifically to handle 3D vector rotation. They use 3 rotational units, j, h, and k, where each one is defined as the square root of -1 and represents a rotation in one of the 3 planes, west, y, yz, or zx. The problem is that Quaternions break a fundamental rule of algebra, the commutative law of multiplication.
What does that mean in physical terms?
In our general number system, a times b is the same as b times a. The order doesn't matter.
Right.
But if you're performing 3D rotations, the order absolutely matters. Think about rotating a cube 90 degrees around the x-axis and then 90 degrees around the y-axis. The final orientation you get is completely different than if you do the y-axis rotation first and then the x-axis rotation.
So the algebraic expression has to reflect that non-commutative reality.
Precisely. Steinmetz notes that mathematically, the product of the 3 rotors is jhk equals +1. But if you change the order, you find that jhk equals khj. This means that the rules of algebra, the ones that let you cancel terms and maintain equality, are violated. If you treat these symbols as simple algebraic quantities, you can erroneously conclude that +1 equals -1.
Which is a problem.
It's a huge problem. Because Quaternions demand this non-commutative approach, which Steinmetz called super-algebraic, they were deemed unsuitable for the speedy, general calculation required by industrial engineers. They needed reliable, straightforward application of basic algebraic rules. So the general number remains superior because its 2 dimensions are sufficient for AC phase analysis, and it maintains that crucial algebraic consistency.
We spent a good amount of time on steady-state alternating current, which is periodic, but electrical engineering is full of these moments of transition when you flip a switch, when a fault occurs. These are transient phenomena, and they're governed by change over time, which means we have to pivot to differential equations.
That's the crux of this next section. The core mathematical structure of practically every time-dependent electrical problem involves a relationship between a function like current, I, or electromotive force, E, and its differential coefficients.
The rate of change.
Exactly, its rate of change. Circuits that contain inductance, which resists a change in current, and capacitance, which resists a change in voltage, they immediately lead to these relations involving first or second differential coefficients.
And to solve these, Steinmetz introduces a method that seems a little archaic, but leads to one of the most fundamental constants in nature, the method of indeterminate coefficients.
It's profoundly elegant. To solve the really simple differential equation to dn x y, which basically just says a function is equal to its own rate of change, we assume that the solution, y, can be represented by an infinite power series. So y equals a0 plus a1x plus a2x, and so on, where all the coefficients are unknown.
So we're basically just betting that the solution looks like a polynomial, and then we let the math tell us what the true nature of that polynomial is.
Exactly right. By substituting this series into the equation and then forcing the resulting expression to be an identity for all values of x, you could solve for the coefficients one by one. You find that a1 has to be equal to a0, and a2 must be a0 divided by 2, or a0 over 2 factorial, and a3 must be a0 over 6, or a0 over 3 factorial, and so on.
And what the math reveals is just astounding.
It reveals the infinite series definition of the exponential function. Y equals a0 times 1 plus x7 2 plus x7 3 plus x3. And that quantity inside the parentheses is defined by mathematicians as x.
The natural base, E, approximately 2.71828, it emerges naturally from the simplest possible equation that defines change. That's why we call it the natural base.
Precisely. And the solution to the slightly more general equation, dx e0, say, is y equals as arrow b8. Because change is so central to inductance and capacitance, the exponential function is, he says, one of the most common functions met in electrical engineering problems. It dictates how quickly a motor speeds up, how quickly a capacitor charges, and how quickly a surge dies out.
Let's ground this in hard physics with the example from the source. The field current rise in a direct current shunt motor. This is a perfect illustration of a transient event governed by this exponential law.
It really is. When you switch on a DC motor, the field circuit is essentially a resistor, R, and a very large inductor, L, in series. The inductor resists that sudden change in current, which means the current doesn't just jump instantly to its final value, A, it rises exponentially.
And the governing equation for that voltage balance is fundamental, right? E equals Rho plus L dt.
Correct. That LDD term is the back electromotive force. It's the transient force that's resisting the current's attempt to rise.
In the solution.
When you solve that differential equation for the current I over time t, the solution is I equals I0, 1e, or LT. And that quantity LR is the time constant, which defines the speed of the transient event. A large time constant means the current takes a long, long time to build up.
And the text gives us concrete numbers for a 500-volt, 50-kilowatt motor field.
Yes. In this example, the resistance R is 250 ohms, and the inductance L is a massive 640 henries. This inductance is built up from, I think, 16,000 total turns of wire designed to maximize the magnetic flux. So based on these numbers, the time constant, LR, is 640 divided by 250, which is about 2.56 seconds.
2.56 seconds doesn't sound like a lot, but in electrical terms, that's an eternity. That's a very slow ramp up.
It is. And Steinmetz calculates the time required for the current to reach 90% of its final steady-state value, which is 2 amperes. Plugging this into the exponential formula, he finds that the current takes approximately 6 seconds to nearly reach its full strength.
6 seconds. Think about the implications of that for operation. If you're designing an automated system that depends on that field being fully energized, you have to account for that 6-second delay, which is entirely dictated by the exponential function.
This is exactly why fluency in solving these equations isn't some academic nicety. It's a practical necessity. The exponential function is the language of inertia in electrical systems. It governs whether your protective relays trip too early or too late, or whether your machine starts up correctly. It's what turns the abstract math into concrete design parameters.
Okay, since we've seen the math for things that disappear, these transient waves, we need to talk about things that last forever. The persistent, periodic phenomena like alternating current. While we all love to assume that AC voltage and current are these simple, beautiful sine waves, Steinmetz assures us that in practice they are always distorted.
They are rarely, if ever, perfectly sinusoidal. This distortion comes from a lot of sources.
Yeah.
The mechanical construction of the generator, the nonlinear magnetic properties of the iron in transformers, or even sudden changes in the load. And if the wave shape is distorted, calculating the relationship between voltage and current using that simple vector algebra we talked about becomes invalid.
The engineer's mission, therefore, is to perform wave analysis. So how do we take an ugly empirical curve, say, from an oscillograph tracing and make it mathematically useful?
This relies on the power of the Fourier series, which is a concept totally central to Steinmetz's approach. The Fourier theorem states that any symmetrical, univalent periodic function like an AC wave can be perfectly represented by a trigonometric series. This series is an infinite sum of a fundamental sine wave, which is the primary frequency, plus its integer multiples, which we call harmonics.
Right, so the series looks something like y equals a0 plus a1 cos t plus v1 cos plus a2 cos 2 and so on.
Exactly, and the engineer's job is to use the empirical data like tables of instantaneous voltage readings over one cycle, and then use some sophisticated integration and averaging techniques to determine the coefficients, the n and bn values, for the fundamental wave and for each significant harmonic component.
Why is this analysis so vital? I mean, if the harmonic components are usually just a small percentage of the main wave, can't we just ignore them?
You ignore them at your own peril, particularly in high-voltage transmission systems. While a harmonic voltage might be small, the impedance of the line components, specifically the capacitors and inductors, is dramatically dependent on frequency. And this leads to the critical danger of resonance.
Let's use a simple analogy here. Why does frequency matter so much in a circuit?
Okay, think of the circuit elements as pipes and filters. Inductors, like the coils in a transmission line, act like a filter that blocks high frequencies. That's because inductive reactance, XL, increases directly with frequency.
Okay.
Capacitors, like the line's capacitance to ground, do the exact opposite. They act like a filter that prefers high frequencies, because capacitive reactance, XC, decreases as frequency goes up.
So you have these two opposing effects.
Right. And if a small harmonic frequency, like the 5th or 7th, is present in the voltage wave, and the natural resonant frequency of that line section happens to be close to that harmonics frequency, the capacitive and inductive reactances can actually cancel each other out. That drops the circuit impedance for that specific frequency to near zero.
Which results in
A massive surge of current at that harmonic frequency, even if the initial voltage harmonic was tiny.
And this is what makes the detailed example from the source so dramatic, the transmission line charging current. Walk us through this critical failure scenario.
Steinmetz sets up this really complex application. A 60-mile transmission line that's being fed by a generator, producing a voltage wave that's slightly distorted with third, fifth, and seventh harmonics. The fundamental effective voltage is 25,400 volts.
But the harmonic terms are relatively small, right? Something
Yeah.
like 12% and 23% of the fundamental.
Exactly. They seem small. The line has certain parameters: resistance, inductive reactance, and capacitive reactance. And because of the capacitive coupling of the line's impedance for the higher frequencies is incredibly low. When the engineer solves the resulting differential equation for the charging current for the entire series simultaneously, the results are startling.
What happens to the current's wave shape?
The calculated charging current is enormously distorted. The higher harmonics, which were small in the voltage, completely dominate the resulting current wave. The effective current magnitude skyrockets. And Steinmetz notes that the fifth and seventh harmonics in the current have such huge magnitudes that the wave shape could make using those machines uneconomical or even unsafe. The line is basically acting as an amplifier for these higher frequency components.
So this moves from being a theoretical inconvenience to a real, actual danger. The distortion is so severe that the current isn't just slightly dirty, it's entirely reshaped by the harmonics.
And the subsequent calculation shows the potential for catastrophic voltage magnification. Steinmetz then considers adding a simple reactive coil in series with the line to limit the current. Since this distorted current is now passing through this coil, the voltage across the coil, E, has to be calculated by multiplying these high-frequency current components by the coil's reactance, which is also frequency dependent.
And since the current is dominated by high-frequency components, the coil's reactance is going to be much, much higher for those waves.
Exactly. The final effective voltage across the coil is calculated to be approximately 119.4 times X, where X is the reactance. Now, you have to contrast that with what the voltage would be if the current were a pure sine wave.
And what would that be?
Only about 9.3 times X.
That is a huge difference.
The wave distortion caused the voltage across that reactance to be increased 12.8 times. If X is large, this means the voltage across that coil can severely overstress the insulation, leading to breakdown. Furthermore, the voltage wave shape across the coil becomes dominated entirely by the seventh and fifth harmonics. The fundamental wave has practically vanished. It's the ultimate proof of why you need harmonic analysis when designing high-voltage systems. A small distortion at the source can lead to overwhelming destructive magnification somewhere else in the system.
We've covered the theoretical framework then: complex numbers, exponentials, Fourier analysis. Now Steinmetz brings us back to earth with the harsh reality of engineering practice. Finding the optimal solution, which usually means finding the maximum or the minimum of some function.
And engineers are constantly searching for these extrema, maximum efficiency, minimum material usage, maximum power factor, minimum heat loss. Mathematically, the process is pretty straightforward. You take the function, you find the derivative, you set it to 0, and you solve for x. That gives you the point of zero slope, the maximum or the minimum.
But once again, Steinmetz demands that the engineer apply physical judgment. Why might a mathematically correct maximum have absolutely no engineering meaning?
Because the mathematical result exists in this abstract, unconstrained universe, while the engineering problem is constrained by physics and by cost. The mathematical solution may fall completely outside the range of physical possibility. For instance, if you're trying to maximize power output, the math might tell you that the true maximum occurs if the circuit resistance is negative.
Which is impossible.
Right. Since negative resistance is physically impossible without active sources, that mathematical result is totally irrelevant to the practical operation of the system.
And he illustrates this with the example of an alternator operating under a non-inductive load.
Yes. In that case, the mathematical calculation for maximum power might suggest an output of 1,500 kilowatts, even if the machine is only rated for a 500 kilowatt full load. Or the equation might show that efficiency continuously rises towards some theoretical maximum that requires infinite current or infinite load resistance. The efficiency is, mathematically asymptotic to the maximum point, but in practical operation, the machine runs far, far below that theoretical optimum because of thermal or material constraints. The engineer has to know the physical limits, like the positive bounds of resistance and current, and ignore the beautiful but meaningless algebraic maximum.
This need for physical realism leads directly to Steinmetz's focus on the efficiency of the numerical calculation itself. It's just inefficient to calculate down to the fourth decimal point if your input parameters are only good to the first.
Reliability and speed were his watchwords. He carefully defines 3 different levels of accuracy that an engineer needs, and he stresses that you have to choose your tools based on the final required tolerance.
Okay, tell us about those 3 levels of precision.
First, there's estimation. Here, a really wide margin of error, say 25% to even 100%, is acceptable. This is used for rough sizing, like figuring out the capacity needed for lightning arresters, or the general magnitude of a short-circuit current. You just need a fast ballpark figure.
Got it.
Second is approximate calculation. This is the bread and butter of design work, where an error of 1% or a few percent is tolerable. And why? Because the materials you're using, the copper winding, the iron core, they already have manufacturing tolerances and variations that introduce that much uncertainty. Calculating beyond this level of accuracy is just a waste of time.
And the third?
Finally, we have exact engineering calculations. This is only required for final performance figures, typically for contracts or guarantees like calculating the final efficiency or the regulation curves of a machine. These calculations demand accuracy down to 0.1% or even higher because these numbers are often legally and contractually binding.
That tiered approach must have saved an immense amount of time for early electrical firms. What tools did he advocate for to get that speed without sacrificing the reliability you needed?
He was a huge proponent of the slide rule, noting that it offers accuracy within about 0.5% when it's used intelligently. This is perfect for that approximate calculation stage. For higher accuracy, he strongly preferred using 3-decimal logarithmic and trigonometric tables.
Why specifically 3 decimals? Wouldn't, say, 7 decimal tables give you better accuracy?
They would, but they're incredibly slow to use. The 7 decimal tables require turning through many pages and interpolating complex values. The beauty of the 3 decimal tables, Steinmetz noted, is that they can usually fit on a single page, which makes the calculation very much more expeditious. For the typical 1–2% accuracy required in design, the speed you gain by using a single-page 3-decimal table vastly outweighs the negligible gain in accuracy from the cumbersome 7-decimal one. The key is to use tools whose precision matches the problem's needs and not to exceed them unnecessarily.
The ultimate check on an engineer's reliability, though, rests not just in the calculation but in its communication. Steinmetz dedicated space to the engineering report, which is so crucial for success and recognition.
He was a master of communication and, really, stakeholder management. For any major investigation, he said, an engineer needs to prepare 3 distinct reports, each one tailored to its audience.
What are they?
First, the general report. It's short, concise, maybe 20–40% of the length of the next one. It only discusses the problem, the purpose, and the final solution. This is for the non-engineers management, financial bodies, clients who just need the bottom line.
Okay.
Second, the general engineering report. This is a moderate-length document containing key data and assumptions, and it should be perfectly intelligible to professional engineering peers. And third, the scientific record. This is the detailed, elaborate, and lengthy document with every piece of data, every theoretical derivation, the complete calculation methodology. It's the resource for future scientists or engineers who need to continue or verify the investigation.
That's a powerful lesson right there. Your audience defines your level of detail. And finally, linking all these methods together, the theory, the tool usage, the communication, is the ultimate rule of engineering calculation.
Yes, the absolute rule is this. Absolute reliability is paramount. And Steinmetz makes a very stark contrast here. If a scientist makes an error in a numerical illustration, the theory might still be sound. But if an engineer makes an error in calculating a bridge truss or rotating mass, the consequences are immediate and disastrous. The bridge collapses, or the rotor flies apart.
Wow.
So reliability is achieved not just by using the right math, but through meticulous process. Neatness, performing every operation twice, and if possible using a different method, like a slide rule check against a log table calculation. Making a rapid approximate calculation first to catch gross errors, and finally plotting the result. If the calculated points don't form a smooth logical curve, the entire calculation is suspect and must be repeated from scratch. That final visual check is the engineer's last failsafe.
We've charted this incredible journey that Steinmetz laid out for the electrical engineer. We started with the philosophical necessity of inventing the general number to represent 2D vectors, moved through the power of exponential functions to calculate time-dependent transients, and saw the serious practical dangers lurking in distorted alternating current waves, a field unlocked by Fourier analysis.
Steinmetz took these really complex mathematical fields, complex variables, differential equations, infinite series, and he grounded them firmly in physical reality. His work provided the exact, efficient, and reliable language that was needed to move from small experiments to the massive interwoven electrical grids that define the modern industrial world.
And the ultimate theme, it seems, is this constant tension, this negotiation between mathematical rigor and hard physical constraints.
It's the essential difference between pure math and engineering math. The general number provides an incredibly elegant solution to 2D vector analysis. Yet, as we saw, the moment we try to move to a 3D rotation, the simple algebraic rules just break down. The simple mathematical product of current times voltage, I times E, is mathematically sound but physically irrelevant for power flow.
Right?
The necessity for the engineer is to constantly apply critical judgment. They have to ask at every single step, does this mathematical result correspond to something that can actually exist in the physical world I am trying to build?
The ability to translate that abstract J into a concrete 90-degree rotation is the magic that really defines this entire era of engineering.
And that leads to a provocative final thought for you, the learner. Steinmetz solved the problem for 2D vectors and time-based phenomena using the algebraic elegance of the general number and the differential calculus of the exponential. But how do engineers today handle problems that are far more complex, like electromagnetic field propagation or highly nonlinear material interactions, where even the most advanced techniques of Steinmetz proved insufficient? The mathematical language is always evolving to meet the next impossible physical challenge.
With that foundational knowledge of the mathematics that built the grid, you are now well informed. Join us next time for another deep dive into the sources that shape